Types of solutions. Let's think about two different solutions that we're familiar with, salt water and sugar water. Remember, a solution is a homogeneous mixture. So salt water is sodium chloride and water, and sugar water is C12H22O11 and water. They're homogeneous. You might say, well, they seem to be pretty much the same, but they have some important differences. But what happens when you stir either of these into water is they appear to disappear, right? The solids seem to disappear, but they're really dissolving. How does that dissolving process happen? Well, there are interactions between the solute molecules. So here's our illustration over here. Let's pretend this is the sodium. No, let's pretend this is the sugar. So here, these blue balls are representing the sugar molecules. There are interactions between them. That's why sugar stays together as a solid at room temperature, because the molecules are attracted. And we're going to learn a lot more about that later. There are also interactions between the solvent molecules. That's why the water stays in the bottom of the cup and doesn't fly away as a gas. And then there are also interactions between the solvent molecules, the water, and the sugar molecules. Whether something dissolves or not depends on the relative strengths of these three different interactions. It's a rather complicated subject, and you can't just readily predict it by looking at the periodic table or something. But if the attractions between the solvent and solute molecules are enough to overcome the solute-solute interactions and the solvent-solvent interactions, then everything will mix together. One analogy that I sometimes use for these interactions is it's like a language. So I am Swedish, my husband's Japanese, and so I can pick on those two nationalities without being accused of being racist, right? So let's say that these are some Swedes, and they only speak Swedish. And these guys are Japanese, and they only speak Japanese. Is there going to be much interaction between these two groups of people who don't speak a common language? No. So if you had a big room full of Swedes and Japanese who didn't speak anything but their native tongue, what would happen? You'd have, at the very least, clusters of people, right? They're not going to mingle because they can't communicate with each other. And that's a little bit like what happens with these molecules. Now, the truth is, most Japanese people and most Swedish people also speak English. So now, if we modernize this and all those Swedes and Japanese speak English, are they going to mix it up and mingle around? Sure they are, because they can interact with each other. Okay? So that's my analogy for solubility. We're going to get a little bit into these interactions. So this is an illustration of a water molecule. It's a little different than the ones we've been shown before. This is the oxygen atom, and these are the hydrogen atoms. And there's an uneven distribution of the electrons within the molecule. We'll get into why that is later. But the bottom line is one end of the water molecule has a partial negative charge. It's not an ion. It's got a partial charge. Maybe it's 0.3 of a full charge. Partial. The other end is partially positive. Okay? So if we put sodium chloride, which is an ionic compound, into water, we have sodium ions are positively charged, and negative ions, the chloride ions, are negative. Well, the positive end of the water molecule is attracted to the negative end of the chloride molecule. They speak the same language of charge. And the positive, did I do that backwards? The positive end of the water to the negative ion, the negative end of the water to the positive ion. Opposite charges attract each other. So there's interaction here. Because water has this charge on it, positive on one side, negative on the other. Each molecule is neutral, but it's kind of lopsided in terms of charge. It can communicate with the ions and make them feel comfortable. And so what happens is we get the negative end of water molecules being attracted to a sodium ion. And so, here's the original salt crystal, and the water molecules come up. They're like, oh, hey, we like you. Come out and play with us. They're like, oh, I don't know. I'm really attracted to my fellow ions here. Oh, but you'll be attracted to us too. And so they surround him, and they replace that force of attraction. They actually do sound like that. Haven't you heard them? The attractions between the partial charges on the water molecules and the ions take the place of the interaction that the positive and negative ions had in the ionic compound. And that's how an ionic compound dissolves in water. It's able to communicate with the water molecules and essentially gets surrounded by them and carried off. And they float around, and you have a homogeneous mixture. Because this solution has ions, it will conduct electricity. Those ions are free to move throughout the solution. Solid ionic compounds do not conduct electricity. Electrical current, is the flow of electrons. It's a flow of charges. If the electrons can't move over distances, not just within an atom or molecule, but over measurable distances, you get no electric current. But when these ions are dissolved in water, this ion can travel to the top of the beaker or the bottom of the beaker, and it can carry electrical current. So a substance that forms ions in a solution is called an electrolyte because it conducts electricity. It's really cool when I can actually do this demo, but it's not going to happen today. If you take a light bulb attached to 2 electrodes and a battery, in most of my other classes we are a little more daring. We just plug it into the wall. And you put those electrodes into pure water, the light bulb will not go on. Water is not a good conductor of electricity. Now, is it still good to avoid water in a lightning storm? Yes, because there we're talking ginormous amounts of volts of electricity, and that can go through lots of different things, and it will conduct. Here we're talking about 120 volts. 120 volts is not enough to go through water. If we pour some table salt in there, haven't changed anything else, pour some table salt in there, the light bulb goes on. In order for the light bulb to light up, there has to be a flow of electric current from this electrode to that one or vice versa. There needs to be something to ferry the electric charges back and forth. The ions are what do that. If we take that same apparatus and put sugar into it instead, sugar also dissolves in water. It will not conduct electricity. The light bulb will not go on because sugar molecules do not form ions in solution. So these are terms you need to know. Electrolytes are substances that dissolve in water and form solutions that conduct electricity. And so these are almost entirely soluble ionic compounds. Non-electrolytes don't conduct electricity. Most molecular compounds are non-electrolytes. What happens with sugar dissolving in water? Well, here's a model of the sugar molecule, sucrose. Now, sucrose has a lot of hydroxy groups, these OH groups on the outside. And these have some polarity. The negative end of the water molecule is attracted to the slightly positive end of this hydrogen, and the positive end is attracted to these oxygen molecules that have oxygen atoms within this molecule that have a slightly negative charge. So they still have a common language, and the sugar is able to dissolve by being surrounded by the water molecules. The interaction between the water and the sugar makes up for the interactions between the sugar and the sugar. And so it does dissolve, but it doesn't form ions, so it cannot conduct electricity. Any questions about that? So we were talking about acids. I forget what day, but this week sometime. And we said that acids are molecular compounds that form hydrogen ions when they're put into water, right? They're molecular compounds, but they ionize in water. So, would an acid conduct electricity in water? Yeah, it will. Some of them do it better than others, and so we have strong acids and weak acids. A strong acid ionizes completely. HCl, hydrochloric acid, is an example. When you put hydrochloric acid that's dissolved in water, it separates completely into its ions. There's no hydrogen chloride molecules left. But other acids are called weak acids. And for them, only a small percentage ionize. So like hydrofluoric acid, there are some hydrogen and fluoride ions, but there are also a lot of hydrogen fluoride molecules still in there. And because only some of these ionize, the number of ions is less, and so it doesn't conduct electricity as well. Acetic acid is another example of a weak electrolyte. A weak acid. So here we have a double-headed arrow, meaning this reaction goes forward, it also goes back. Oftentimes when we have a forward arrow, we mean it goes pretty much completely to the product side. So a strong acid is going to be a strong electrolyte. Strong acids and soluble ionic compounds dissolve completely and form lots and lots and lots of ions. Okay? They conduct electricity well. They conduct electricity strongly. Strong electrolyte, you get a strong glow on that light bulb. A weak electrolyte conducts electricity weakly, with an A, not EE. So weak acids are examples of these. They do form ions, they do conduct some electricity, but they only form a few ions, and so the light is very dim. Here's an example. Here we see a non-electrolyte, and this is a weak electrolyte. The light bulb is on, but it's like you were using the dimmer switch and had it turned way down. And here's a strong electrolyte. So if you're adding the same moles of substance, you'll get a much weaker glow from the weak electrolyte. Questions? Another word, dissociation. So when an ionic compound dissolves in water, the anions and the cations separate from each other, and they mix around in the solvent, the water. And we say that is dissociating. So they're not associating, coming together, they're dissociating, they're going away from each other. So we put sodium sulfide in water, it dissociates into sodium ions and sulfide ions that move around. It's not really correct to say that sodium sulfide ionizes, because as the pure solid, it also includes ions. But the ions dissociate. When we have a polyatomic ion like sulfate, sodium sulfate dissolves in water. We did that in lab the other day. When it dissolves, these ions dissociate. The sodium ion goes off on its merry way. This polyatomic ion stays together as a group. Remember I said those are like bundle packs from Costco. We're buying multiple things and they're all shrink wrapped together. These guys are going to stay together. So ionic compounds are going to separate into two ions. So ionic compound dissolved in water, you've got a solution that contains ions that are separated. Not all ionic compounds dissolve in water. Can you think of one that some of you still have on your benches that does not dissolve in water? Barium sulfate. It's not soluble in water. We're filtering it out, and we had chloride coming through, and so we're rinsing it with some more water. The water is not dissolving it. That's an ionic compound that does not dissolve. So if it dissolves, we say it's soluble. If it doesn't dissolve, it's insoluble. The truth is, though, even insoluble compounds dissolve a little bit. Now, it may be so small that it's just not even important. But I just want to be clear, an insoluble compound, a little bit does dissolve. So let's look at silver nitrate. We've got some of that in the lab today too. We've got silver nitrate. That is soluble. It will dissolve in the water, forming a strong electrolyte solution. The silver ions and the nitrate ions completely separate from each other. It's a little bit like silver and nitrate are a couple, and they came to a party, and they're going to mingle, right? You're like, hey, catch up with you later. And they just mingle around, okay? They're not stuck together. Silver chloride, on the other hand, is almost completely insoluble. You stick silver chloride in water, almost nothing happens. The silver ions and the chloride ions are just so attracted to each other that they're just not going to go out and interact with the water molecules. This would be like that annoying couple of friends that you have. They're a new couple and they're just so infatuated with each other. They may be at a party, but good luck talking to either one of them. They're in the corner making out, right? They're just like joined at the hip, and they're so annoying. So they're insoluble. They may be insufferable as well. So how can we tell if something's going to dissolve or not? Well, it's complicated. It's not easy to predict. And the best method is empirical. It's experimental. Thankfully, other people have already done all these experiments for us. They're like, oh, well, let's see if barium sulfate dissolves. Oh, no, it didn't. Let's try barium chloride. And they just did a whole bunch of experiments, made a whole bunch of measurements. So the result of that is that there are some patterns in solubility. And so different books list them in slightly different ways, but this is what we're going to go with. And this is some information that you should do your best to memorize, okay? So these are solubility rules. We have this first group. These are compounds that are generally soluble. And then in the bottom lists some things that are generally insoluble. So if you have a compound that contains lithium, sodium, potassium, what do those three ions have in common? Where are they in the periodic table? They're all in group 1. Lithium, sodium, potassium. They're all over there, right under hydrogen. So it's those three guys and ammonium, that weird polyatomic cation. Any compound containing those, one of those is going to be soluble. If it has nitrate or acetate ion in it, so like potassium nitrate or cadmium acetate or whatever you have, those are going to be soluble. Over here is a list of exceptions. There are no exceptions. So if you have a compound that's something acetate, soluble. Something nitrate, soluble. If it's got chloride, bromide, iodide, what do those three guys have in common? Same group in the periodic table, right? They're a member of, what's the name of that group? Halogens. These are the ions, and so we call them halides. Bromide, iodide, halides. So the halides, these are generally soluble, except with these three guys. Silver ion, that's mercury 1, and lead 2+. So silver chloride, silver is an exception to the general rule that chlorides are soluble. And then down here, we've got hydroxide and sulfide. Most hydroxides and sulfides are insoluble, but there are some exceptions. So if it's paired with one of these cations, it's going to be soluble, because those guys are always soluble. So you can read that. And there's carbonate and phosphate. So we need to know how to use that table, and you should try to memorize that table. Okay? So if we predict solubility, how do we do that? Here's nickel 2 sulfide. Well, what we're going to do is we're looking in the table for nickel 2 ion and sulfide ion. And so we look through here. Oh, sulfide. Sulfides are generally insoluble. We go over here and see if there's an exception. Nope, nickel isn't one of the exceptions. So then we would say that this is what? Insoluble. I'll just give it a capital I. How about magnesium phosphate? Soluble or insoluble? Insoluble. Down here's phosphate ion. Exceptions, just those halides and ammonium. So this one's insoluble. Lithium carbonate, soluble. Okay, carbonates are generally insoluble, but lithium compounds are always soluble. So it's listed in the exceptions. How about ammonium chloride? Soluble, insoluble? Soluble. After you do a few examples, the rules are really not that hard to remember. Any questions? Remembering the solubility rules will not be a huge deal. Okay, it's a little deal.